All right, so for this daily problem, we have these three molecules, and we had to figure out which one had the highest boiling point and which one had the lowest boiling point. What do you guys think? Which one of these has the highest boiling point?
Pentane.
One to the left. You say this one has the highest.
Yeah.
All right, which one had the lowest?
The neopentane.
Neopentane. Why did neopentane have the lowest?
Because it has the least surface area.
So what about its surface area?
It's the surface area for it is like the last.
Right, so there's the smallest amount of surface area for this compound, which means it could actually have a lot less dispersion interactions because we can't shift the electron density around as much. If we look at pentane, which is a long aliphatic chain, it has a lot more surface area and it can be polarized a lot more. Now the other thing to think about is the way I look at this is if we have some molecules, we're trying to kick them into the gas phase, right? Let's say we have kind of a cubic room, and we have our molecules in here, and we're trying to kick them out of the room. I see these ones more shaped like pool noodles, and then these guys more shaped like beach balls. If you're trying to pick them up even and trying to throw them out of the room, the pool noodles are going to touch against one another, get intertwined, and hard to move around, right? Whereas these guys you can easily kick out because they're spherical shaped. So does that make sense to everybody on why this one will have the highest boiling point? Yeah, maybe? The highest boiling point. This guy will have the lowest boiling point, and then the one in the center is in an intermediate state. So you can actually go, how many people Wikipedia'd the boiling points for all of these and determined it that way? Nobody? Oh wow, okay. There we go, see, that's using your head. You should be doing that. That makes sense. You have a literature for you. Why wouldn't you do that? And then you know the correct answer. See, I see nothing wrong with that. That's using your head. All right. So last time we finished up talking about solids. We're going to jump to liquids for a little bit, and then for the rest of today we're going to talk about phase diagrams, where it's a graphical way to represent phase changes. And there's some kind of interesting points with that. Some things called supercritical fluids. They're kind of strange. It's actually how they make caffeine-free coffee. If you're ever curious.
That's awful.
Yeah, I know. Why would you want to even do that? That's the only benefit of coffee. So let's talk about changes in state, and then we'll get to phase diagrams. And the first thing we're going to talk about is vapor pressure. Vapor pressure. Crazy. Does anybody else hear that?
Yeah.
Sorry, now I brought it to your attention. So what it is it's an equilibrium between the gas phase and the solution. Because you know, if you leave some water out, if you give it a long enough time, what's going to happen to your water? Like liquid water. It'll evaporate given enough time. That's because an equilibrium hasn't been established between the liquid and the gas phase. So all liquids exhibit a vapor pressure. So it's an equilibrium, which is a word that we're going to use a ton in the upcoming semester. Equilibrium pressure between liquid and gas if we have a closed system. In a closed system. All right. And it depends on the atmospheric pressure that's being exerted on the liquid. So if you, like let's say you had a glass of water and you were at sea level and you went up to a mountain, they would actually exhibit different vapor pressures. Those in general chemistry, you guys actually did an experiment where you were trying to prove the ideal gas law. And I had to go look at the barometer to see what the pressure was, or else your math was totally off. Sometimes you'll have to do that depending on what type of experiment you're doing, if you're looking at gases or you're looking at liquids. So, it depends on temperature, and on atmospheric pressure. All right, so what do I mean by this? Let's say we have time is equal to 0. We're going to have a time is equal to 0 state, and we're going to have some time later on. We'll have time is equal to infinity, so to the end of time. And we'll have a flask in here. So we'll draw our little flask.
What's in the flask?
What's in the flask? Were you not doing a dime joke? What is in the flask? We have some liquid. There we go. And we'll cap this guy. So cap it, we put a stopper on there. That's my fancy stopper. Bless you. And we'll put a liquid. I guess it's going to be a red liquid. Or maybe blood.
Blood.
Or fireball, so. All right, we're gonna fireball in there. All right. And now, initially, as soon as we dump the liquid in and we cap it, let's think of the tiny microscopic events that are happening here. So there's really no liquid. Let's call this, we'll pretend it's water because that's easier, because then I don't have to say fireball over and over again and sound like a wizard. Instead, we're going to have our water. And at the start, let's assume we're in a really dry climate. There are no water molecules in the air or in the gas phase. So as soon as we dump it in, what's going to happen? Well, some of the water particles are going to try to escape into the gas phase. So some of these guys are drawn as little circles. They're going to pop out into the gas phase. Now, what about when time hits infinity? Or we've given enough time to reach equilibrium? What's going to be happening? Yeah. Yep, it's going to go back and forth. The air is going to be saturated with the gaseous form of our liquid. And what happens is as gas phase particles are condensing into the liquid, some of the liquid particles are going to be going into the gas phase, and we're going to reach what's called an equilibrium. So some of these guys are going to come popping out, but at the same time, we're going to have some going from the gas phase back into solution. All right, so at the start, our liquid particles are going to diffuse into the gas phase. So liquid particles diffuse into gas phase. And then at time is equal to infinity, we've reached an equilibrium. So equilibrium reached. Bless you. Between gas, and liquid. Okay, so an equilibrium has been reached, which will become a really important topic later on. So keep that idea of equilibrium in your head. All right, so now whenever we go through a phase transition, like let's say we go from a solid to a liquid, what do we have to do to be able to actually do that? What do we have to put into the system?
Energy.
Yeah, we have to toss in energy. Let's say we wanted to do the reverse. Let's say we want to go from a liquid to a solid. What do we have to do?
Remove energy.
Yeah, we got to remove energy. These go by special names: heat of fusion or heat of vaporization. So we're going to talk about those. Let's talk about the heat and vaporization first. Vaporization. Delta H vape. What is H again in terms of thermodynamic properties? Or state functions, excuse me. You remember from last semester? Yep, it's enthalpy. How does enthalpy differ from energy, do you remember? There's just a pressure volume term added in there. That's all. So that pressure volume term accounts for a constant pressure but a change in volume. And that's just something we assume. Random thermodynamics stuff. All right, so jeez.
Do you vape?
Apparently I vape. I sound like it. All right, so heat of vaporization, what is it? Well, it's the amount of energy required to go from a gas to a liquid. So amount of energy required to vaporize 1 mole of a liquid to a gas.
Is there a different name to it from a gas to a liquid? Or is it the same
From
thing?
a gas to a liquid? Yep. Well, actually, we'll talk about that in a moment. Okay, so we have, we're going from a liquid to a gas. Let's consider the change in enthalpy. And let's compare it to 0. Is the change in enthalpy going to be greater than or less than 0? Greater than, you say. So we have to think about is that an endo or an exothermic interaction? Yep, it's endothermic. So does that mean delta H has to be positive or negative? Positive. So what does that mean? Is that greater than or less than 0? It's greater than if it's larger than 0. All right, what about if we go from a gas to a liquid? What about delta H compared to 0? Is this an endo or an exothermic process? Yep, it's exo. We have to give off energy so our gas phase particles can quit moving around so much, condense out, and become a liquid. So in that case, delta H is what compared to 0?
Less than.
Yep, less than. It has to be a negative value, because if we have a negative value, we have an exothermic reaction. Okay, then let's talk about heat of fusion. Heat of fusion, it's almost the exact same thing. Fusion, delta H fuse. It's the exact same thing, except it's the amount of energy required to melt 1 mole of a solid to a liquid. So delta H fusion, it's the amount of energy required to melt 1 mole of a solid to a liquid. Okay, so now let's consider the phase changes associated with this. We can go from a solid to a liquid or a liquid to a solid, and then we're going to keep track of delta H. All right. So if we go solid to a liquid, then we'll have liquid to a solid. Consider delta H 0, delta H 0. So going from a solid to a liquid, is that an endothermic or an exothermic process? Yep, it's endo. If it's endo, what about the sign of delta H, positive or negative?
Would be positive.
Yep, it's got to be positive. delta H is positive for an endothermic reaction. Is it greater than or less than 0? Yep, greater than. Then what about going from a liquid to a solid? Yep, less than. Okay, so let's see an example of this. Example. A heat of fusion. Of H2O, water, is positive 6.02 kilojoules per mole. What is the change in enthalpy when 7.29 grams of water freezes? Green. Okay, what are we looking for in this problem?
The change in enthalpy.
Yep, trying to get the change in enthalpy. What information is important to us?
Probably the amount, 7.29 grams.
Yep, this amount. What else?
Probably the amount of energy.
Yep, heat of fusion. Okay. What number are we going to start with?
We have to figure out how many mole.
Grams. Yep, we have to figure out how many moles. So let's take this 7.29 grams of H2O. We got to multiply this by a conversion. What unit has to go down in this denominator? Grams. Because we need grams to cancel out with grams. What goes up top? Yeah, we got moles in that case. Moles of H2O. For every 1 mole of H2O, how many grams approximately do you have? Yep, 18.015. 0.15 grams. And that just comes off the periodic table. All right, so we're out of grams, we're into moles. Where do we go now? Well, are we at our answer yet? No, okay. Get a bit closer. What unit has to go down here? Yep, moles, H2O. What are we going to convert to up top? Yep, kJ, kilojoules. What number is going to go up here? Yep, 6.02. What number is going to go down here? 1. Okay, when you multiply that all out, what I get as a result is 2.44 kilojoules. Is that the correct number of significant digits? Yeah, we're good. All right, now let me ask you, is that the answer? No, why?
That's for the change of enthalpy.
It's freezing. So what's that mean for you? Yep. We have to keep track of the phase transition that's happening. We're going from a liquid to a solid. Delta H has to be what then? Yep, it has to be negative or less than 0. Therefore, the change in enthalpy for our reaction is going to be negative 2.44 kilojoules. And that's the answer that we want to report. Does everybody see why? Yeah? No? Maybe? Thumbs up? Just give me a thumbs up, we're good. All right, so let's talk about phase diagrams now. Those are a little more interesting. I'm just talking about heats of fusions. And heat capacities and whatnot. All right, so phase diagrams give a nice graphical way to represent phase transitions. And, it's actually kind of interesting. If you even look at water, and we have one liquid phase, we have one gas phase. Do you know how many phases of solid water there are, or crystalline water? 2? Nope, more than that. How many? 7, more than that.
10.
More! Keep it going.
Purple.
Purple. Purple is a pretty close.
Oh, yeah.
So the question is how many different phases of solid water are there? Well, we don't really know. Right now we know that there are more than 54 of them. We have 54 of them identified. But there are 54 unique different structures of water, which is crazy. So how do we keep track of all of that? Well, we do it through these phase diagrams.
How are there 54?
Think about all the different arrangements of all the possible water molecules you get. And also, we have to keep track of pressure. We're going to keep track of pressure and temperature. And we actually, if you look at the water that's on Jupiter, it's water X. That's what it's called. And it actually forms little X-like structures in the solid. It's kind of strange. When you squeeze stuff, things behave really, really weird. Let's talk about the really, really weird. When the going gets weird, the weird turn pro. You know who said that?
You.
Yeah, I did just say that. Do you know who the man known for that quote?
Gandhi.
Nope, Hunter S. Thompson. You should look him up. He's an awesome dude. Well, was an awesome dude. All right. So let's talk about the normal boiling point first. And we've talked about this, I think, once or twice. Does anybody remember what the normal boiling point was? Or could you give me a working definition? We can build on it. So boiling point, yeah, go for it.
The boiling point of a substance under normal atmospheric pressure.
So what do you mean by normal atmospheric pressure?
What we concerned.
Yep, 1 ATM. 1 ATM is the thing. So the temp at which the vapor pressure of a liquid is 1 atmosphere, 1 ATM. And I bet you can guess what the normal melting point is, or what special parameter we have to have there. What do you think about the pressure there? Well, it's not the vapor pressure, because solids can't have vapor pressures, right? What it is it's the temp at which the solid and the liquid states have the same vapor pressure conditions, where the total pressure between the solid and the liquid is 1. Is 1 ATM. Because even if you take solid water, some solid water, actually some of it is immediately going into the gas phase. It has enough kinetic energy where it can escape out of the solid and go directly into the gas phase. All right, so we know a little bit about that. Let's actually start drawing some phase diagrams. So what is a phase diagram? What it is it's just a graphical way to keep track of the different phases, keeping track of pressure and temperature. So graphical way to represent phase changes of a substance as a function of temperature and pressure. Okay. Bless you. All right, so what we're going to have on our y-axis is pressure. And on our x, I'm going to have temperature. If I would want to be proper, I should put units here. We'll do Kelvin for temperature. Well, for pressure, we'll do ATM.
Why'd you have to pick Kelvin?
Kelvin? I like Kelvin.
I don't like Kelvin.
Why not? What do you ever do to you? Alright, and we're going to get some lines, and what these lines are, they're different phase transition lines. I'm going to draw them in different colors because they're different phase transitions. You may choose to do dots or squigglies or something. So we're going to have one line that goes to here. We'll go with baby blue. The next one. That. Race car red. Yeah.
You're supposed to make that with Drew.
Yep. Well, actually, it depends completely on the substance. This one is, I believe, for water, so it's a little different. All right. So let's think about the different phases in these different regions. So over here, we have it when the pressure is really, really high and the temperature is low. What phase do you think that's going to be? Yep, should be a solid. Yeah, solid over here. What about when the temperature is really high and the pressure is really low? What phase do you think we're going to have? Yep, we'll have a gas in that case. Okay. What about in between? Liquid, very good. Okay. Oops. And there's a special point on this plot. At this point right here. Does anybody know what that's called? What'd you say, Tim? I'm sorry, I didn't hear you. Ooh, I've never heard that. That's a fancy $5 word. Can you describe what happens at that point?
That's something I learned in another class with like iron, carbon-based iron. I don't know if it applies to you, but it's like where it goes directly from a solid to a liquid. I don't think it applies.
Okay. I don't know that. I've never heard that term before, so I'm kind of interested. I'll have to look that up. What I have always known this as, this is the triple point. This is the triple point. Triple point. And it's a very strange spot. It's where you cannot really distinguish the difference between a solid, liquid, and gas. They're all happening at the exact same time, which is really weird. You don't get to see it too often. The kind of strange thing is you have really weird behavior at that point too. All right, so let's talk about each one of these lines. We're going to label this line 1. We'll label this one. Oops. Yeah, we'll go with 1. We'll do 2, and we'll do 3. All right. Line 1. What would you call that event if we were? Well, it's basically the solid gas line.
Sublimation.
Yep. Sublimation. So if you decided to stick at this pressure and went to this temperature, you'd be subliming. You'd be going from a solid to a gas. What about 2? I'm going to call that the solid liquid line. Oh, what, sublimation, and what's the opposite of sublimation? Okay, we'll hop back to it, we'll let people think. Solid liquid line. Yep, melting. And what's the other one? Fusion, or, well, not fusion, that would be melting, right? What about when, so we, solid to a liquid is melting? Yep, freezing. Okay. 3, we have the liquid gas line. What type of events happen there? What's it? Evaporation.
Condensation.
Condensation. Okay. Do you remember what the top one is for the solid gas line? Yeah.
Deposition.
Yep, it's deposition. Did you have to look back in your notes, or did you know it?
I didn't say it loud enough the first time.
Oh, okay. Sorry. Deposition. Yeah. Good. Okay, I didn't get yelled at. We're fine. All right. And depending on whatever substance we have, we'll actually get completely different phase diagrams. So as an example of this, we'll turn this on for a moment. And we'll check out the differences between carbon dioxide and water. And there's actually something kind of unique about the phase diagram of water compared to other substances. It's a little strange, but we'll see it, hopefully, if that ever comes up. Okay, let's go to the document. Well, the display is still blinking. We can do it. All right, we'll wait. Okay, let's hop this on now. All right. Perfect. Can't see any of it. Here, we'll try this. Better? All right. Zoom it out. All right. So what we have is, we have water on one side, we have carbon dioxide on the other. And kind of a strange thing, carbon dioxide is most like most other substances, where if you notice the solid liquid line, it kind of goes at almost a linear rate. But when you look at water, there's an interesting consequence. This actually dips the exact opposite way. Does anybody know why? Yeah, water has to be different, but why is it different? Yeah.
Because gas molecules are going into solid and the solid water,
So that
and it's
fish
hard to
survives.
test that.
Not quite.
So that fish survives.
Fish, yeah, exactly. So that fish survives. Fish do survive because of this. Why is it though?
Because it floats as a solid.
Right. So why does it float? Yep. What causes that density change?
The structure of the molecule.
The structure of the molecules. So how do they structure? What's that intermolecular attraction force between water molecules that causes that? H-bonds. H-bonds are the reason for that weird taper and why the fish survive in the wintertime. So the reason it deviates